Hello, everyone. I'm Yuhua Zhang from Michigan State University. Today, I will introduce our ICCV 2023 work, Robust Mixture of Expert Training for Convolutional Neural Networks. Let's talk about the MOE first. MOE is widely accepted due to its high influence efficiency in the large model area. And different from the traditional CNNs, MOE activates different parts of the model for different input through a routing system. And this figure gives you a comparison between MOE and the dense network, as well as the pruned sparse network, which is input agnostic, and the corresponding small dense network, which shares the similar parameter number of a single expert of MOE. And MOE consists of pathways and routers. In each layer, the network are firstly split into different experts, and the routers make selection on specific network for each layer, which then make up a pathway. The size of the expert is controlled by the model scale R, which denotes the ratio of a single expert size to the entire layer. And this work focuses on the adversarial training for MOE-CNN. In particular, we know that AT, which is adversarial training, has become a main research topic for normal CNN. However, we still do not know how to robustly train an MOE. The questions remain, will there be more challenges to adversarially train an MOE? Do we need more complex AT recipes? And will there be new insights to help us understand the MOE better through this process? Okay, with these questions, we conduct our warm-up study, the most naive way to implement AT with MOE-CNN. And the results are very negative. As we can see, if we compare it to an adversarially trained small dense network, which is supposed to serve as the performance lower bound, the performance of MOE-CNN is even worse. This means that adversarial training for MOE-CNN is not trivial at all. And intuitively, this result makes sense since the routers of the MOE not only bring the efficiency benefits, but also introduce more robustness weakness. One hypothesis of ours is that to launch a successful attack on MOE, the perturbations can either attack the pathway or the router to lead the model to make mistakes. And this is what we call the two-way attack mode. And the latter to attack the router is unique for MOE. And to verify this, we look into the router robustness by only robustly training a router given a pre-trained undefended MOE model. The result shows that compared to the undefended CNN with a robust mask, the robustified routers are better. However, it is still worse than the robustified small dense models, which means that only robustified routers is not enough. And we further make a dissection on the router and pathway robustness. We particularly look at those cases where the attack is successful. We found that out of the total 62% of attack success rate, the majority of them does not successfully break the routers. This means the routers are okay. However, the weak pathways can still lead to unrobust models, and therefore robustifying routers alone is not enough. Further, we fix the robustified router and robustly fine-tune the pathways, namely the model backbones, and the new result surprises us because when we start to adversarially train the pathways, the attacks can easily break the routers, even if the routers are fixed. This indicates that the routers of the robustness of the routers and the model pathways may be at odds with each other. And this inspires us to look back to the current AT design for MOE, and we find that such a formulation fails at modeling and optimizing the coupling effect between the routers and pathways. Therefore, we advance this formulation to a bi-level optimization problem with a hierarchical structure, including an upper-level problem to train router and the lower-level problem to train pathways. Usually, it is not easy to solve a bi-level optimization problem. However, here we found that alternating optimization works very well, and it is a very simple idea. We just proposed the ADV-MOE, which alternatingly optimize either the routers or the pathways with the other part fixed. And we conduct extensive experiments on various data sets, and we found that ADV-MOE can significantly improve vanilla AT on MOE and also outperforms the dense model robustness. Further, we noticed that ADV MOE can still retain the high inference efficiency, which is the intrinsic advantage of MOE. At last, we studied the effect of different expert numbers and model scales. We found that the comfort zone of the expert number is around 2 to 5. And if the expert number is too large, the training becomes difficult. And also ADV MOE caters to a wide range more experiment results to our paper. And our paper, as well as the code repo, can be accessed through the QR code in this page. Thank you for watching this video.